Hello, welcome to Unit 10, which is Thermodynamics and Equilibrium and Introduction. And congratulations on getting this far. These topics are more of an advanced set. And in this unit, we will be introducing these topics, and we won't be doing a whole lot of math, which may be exciting for some of you and may be disappointing to others. But we're going to cover these and talk about the important concepts involved. Thermo means heat, and dynamics means changes. So how energy changes is a big topic in life, from producing heat to heat our homes, to transportation, to producing consumer goods such as food and clothing. Most chemical reactions are reversible to some extent. So to better understand the relationships between the concentrations of reactants and products, we have to understand this concept of chemical equilibrium. And when we understand that, we can better manipulate the equations to produce products more efficiently, or maybe to negate some of the deleterious effects of chemical change. And this is really important in environmental science and in medical science as well. So let's get to it. Okay, the nature of energy and the first law. Okay, so we'll be discussing here the first law of thermodynamics. And that is, thermodynamics, of course, is the study of energy and heat changes. Energy is the ability to do work and to produce heat. And so when we look at an energy equation a little bit later, we'll dissect the different aspects of energy. And this first law states that the law of conservation of energy can be converted from one form to another, but can neither be created or destroyed. And so that is a big part of this first law of what we call first law of thermodynamics. Okay, so let's talk about the nature of energy in the first law. We talk about kinetic and potential energy when we're talking about energy, and hopefully this is a review for you from some of your other science classes. Kinetic energy is the energy of an object due to its movement. The type of energy is dependent upon the mass of the object and its velocity. So we say kinetic energy is equal to 1/2 the mass times its velocity squared. I always think about football players when I think about kinetic energy. We have created a problem with our football players because football players have gotten more and more massive over time. They've found greater ways of creating very muscle-dense fiber in their bodies. They're very muscular and they're very dense, and so they've become quite massive. And they've also learned, even though they're bigger, they've trained to run faster and faster and increase their velocity. And so when football players hit you these days, they hit you with a lot of kinetic energy. And one of the things that has developed over time is maybe not as quickly as the kinetic energy is the protective equipment. And so there is a push now to create better and better protective equipment to protect athletes from brain injury, from catastrophic injuries to their limbs and so forth. And so this all has to do with kinetic energy. Potential energy is the energy due to the position or composition of an object. In chemistry, we talk about the composition of different substances and their potential energy. One of the great types of chemical potential energy is food. When you eat in the morning, you ingest potential energy that helps fuel you for the day. I had a great big old breakfast this morning, and I'm ready to attack the world because that is going to fuel me through my day and sustain all the different functions as well as cognitive functions that I have to do. When I run out of potential energy, I get hangry. So I get that empty feeling and I get anxious, and sometimes I'm not too pleasant to be around. The nature of energy in the first law continued here. Temperature. Okay, so we're going to talk a little bit about temperature and heat and compare and contrast these. I think we've done this before in other units, but it's good to review it. Temperature is a measurement of the motion of particles, so that's the kinetic energy. Heat is a transfer of energy from one object to another due to temperature differences, usually going from low to high temperature differences. Work is the ability to move an object over a distance. And so this is a little bit different than maybe your definition of work out in the real world. And let's say I got crazy and I decided that I wanted to push a wall down. And I get up on it and I push and I push and I push. And you would think, well, you're doing a lot of work there. Well, actually, you're doing no work at all because you're not moving the object over a distance. And so to do work in terms of physics definitions and chemical definitions, you have to move an object over a distance. Okay, so now we're going to look at the first law mathematically, a little bit differently anyway. And we use this formula, E is equal to Q plus W. Sometimes they'll use the letters delta U, which means the internal or the energy of the universe, but we'll just call it E here. And Q is the component of heat in energy, and W, of course, is the component of work. And so the Q is a little less. You might think H, but they use H for enthalpy, which we'll talk about in more detail as we go along. But Q is the heat involved in the energy component, and then W is the work, or the ability to move an object over a distance. In any system, the energy available can be thought of as the amount available due to work and will be lost as heat to the surroundings. And so I always like to think back about the days when I first got a car when I was 16. My grandfather gave me a 64 Ford Custom 500. And I was so excited to get that car. A lot of my friends didn't have cars. And so I would go and I would pick my friends up and we would run all over town. We'd go and play ball. We'd go visit other friends. And a lot of times we'd end back up at the ice cream shop toward the end of the day. And by the time we got there, the ice cream shop was super busy, so we couldn't find a seat inside. So we would climb on top of the car to eat our ice cream. And of course, we've been driving that car all day, and we've been doing a lot of work. We were moving the car over a distance, right? So the W part was taken care of, but the heat part was not. The engine did a lot of work moving the car, but some of that energy, the gasoline, just went to heat that was lost, and it heated up the hood of the car. And so you could sit up on top of the car for a little while, especially when you first got there. It was very unpleasant to sit on because of all that radiant heat that was lost. And so any system has those components. Even chemical systems, when we mix chemicals up in the lab, well, there's a certain amount of work done against the atmospheric pressure, and then you can capture some of that to do some work. Maybe move a cylinder or a piston. You might cause a balloon to expand if you're catching the gas in a balloon that you made. But there's a certain amount that's always lost to heat, to the environment. If you want to make lots and lots of money, figure out a way of reducing that heat waste and producing more energy that is used for work. So we talk about these systems or these chemical reactions or mechanisms as having different parts. The system is a part of the universe under consideration. In chemistry, that's usually the chemical reaction. The surroundings is everything else in the universe. So in terms of driving that car around, the system would have been the car engine that was doing the work. and then the surroundings would have been the hood of the car, right? And that's where all the heat is lost to. Burning fossil fuels is a highly exothermic reaction, which means it gives off lots and lots of heat. You have certain systems that absorb heat, and we call those endothermic reactions. So in chemistry, we consider the reactants and products to be the system, and the surroundings being the reaction container or the room or anything other than the reaction itself. Heats of reactions. Okay, so the heat of the reaction is assigned the letter Q. We just talked about that. At a given temperature is the value required to return a system to the given temperature at the completion of the reaction. So in terms of this example of the car, it would be the amount of energy necessary to cool that engine off. It would be the opposite of all that energy that was lost to the environment. An exothermic process is one which heat is evolved. Q is negative. The reaction vessel warms and the energy is subtracted. Definitely burning fossil fuels is usually an exothermic reaction. It releases lots of heat into the environment. Endothermic reactions absorb heat, and the Q value is positive, which means that the system absorbs that energy. An example of that would be a cool pack. If you've ever played sports, maybe you've sprained an ankle or had a bump, and they wanted to apply something that was cold to reduce the swelling. Well, they would put a cold pack on there. They break the chemicals up, and that absorbs the heat from the environment, and you get a nice cooling effect on your muscle or your knee or whatever is sprained. Enthalpy. Now, we talked about why Q is not H, right? We didn't say heat is H. We say enthalpy. And this is a very specific energy term used to mean Q at constant pressure. And usually in chemical reactions, when we do chemical reactions, the only pushing back effect or the only thing that we're doing work on is the environment, which has a constant atmospheric pressure. So enthalpy is denoted by H, is when heat is absorbed or evolved at constant pressure. And we use this term QP as our note for that type of thing. This QP here is what we say. We say QP is equal to delta H at constant pressure. And enthalpy is a state function. We'll talk about that in a minute. I also want to point out here that enthalpy denoted H here, denoted H. When we say we have a change in heat, we use letters. We say delta, use the symbol delta H to mean enthalpy, and when it is positive, it's endothermic, and when delta H is negative, it's exothermic. Okay, so and I'm sure we'll catch that on the next slides as well. Okay, so now we're going to talk about the difference between state and non-state functions. Enthalpy, delta H, is an extensive state function that only depends upon the amount of substance or of the entity being considered and is independent of previous history of the system. So you can think of this, a great example of this is altitude. And so we have some skiers up here on a mountain, and the altitude that they've reached before they descend is independent of how they got there. So their distance from the peak of the mountain down to sea level, or the altitude, doesn't depend upon if they snowshoed up there. Maybe they started down at the bottom and they had to make several different bends and movements to get up on top of the mountain, and maybe they had to do travel a lot of distance to get there. Or they could have traveled up on a ski lift and had to travel a whole lot less of a distance. And so this altitude is independent of how they got there. The altitude of the mountain climber is a state function. It is independent independent of distance traveled. Okay. Distance traveled is analogous to a non-state function. So the distance might have been great or might have been small, and that depends upon how they got there, right? So it's dependent of the pathway that they've got there, or the path that they took. And so in the next slides, we will talk more about enthalpy and how we use that in chemical reactions to predict what happens and how much energy can be produced. And so looking forward to seeing you in the next recording.